Okay. Eudora. We wait for the others to come in. Okay. Chen, Dia, Eudora. Okay. Okay, good morning, everyone. So we have 12 participants. Okay. Do you go through the video?
Yeah.
Okay. This topic is start with topic 6. Okay. Sorry about the last lecture, the last video. I forgot to record. So I think I need your help. Every time when we start the class, please remind me to press the record button. I forgot to record. So today is fine. Okay. So we're going to discuss about this oscillation topic. Okay. This is the basic of wave. Okay. So those who went through you watched the video, you might have some information. I never expect 100% understanding. Maybe some. Okay. So this is about. Okay, this is about oscillation. This is the basic of wave. We can start now. Okay, this is the basic of wave. So I think in the video also the same slide. Okay. So you know about oscillations, the back and forth movement. It's a back and forth movement. You can see in this diagram. Okay. So the ripple, the pendulum, the spring, all are oscillations. The clock, cradle, back and forth movement. Okay. So oscillation, if you draw a displacement graph, this is how the graph going to be, displacement versus time. Okay. You see this graph, let's say you have a pendulum. Okay, you have a pendulum. Okay, you have a pendulum in 3 locations. Okay, 1, 2, 3. Okay, the center we call 0 displacement. Okay, this position we call as positive displacement. Okay, because displaced to the right, and the most extreme to the left is called as negative displacement. Negative displacement. Okay. If the time started at 3, the time 0, let's say the time 0 started at the position of 3 means how's the displacement graph going to look like? This is time. This is displacement. Okay, sorry. This displacement. If you 3, the position 3, time 0, the displacement graph going to start with at the center, at the positive displacement or a negative displacement?
Positive.
Positive. So the graph going to start here. Okay. So you're going to make Okay, so when the time 0, when it will be here, then it's going to make go down and it make like this. So you're going to make what type of graph?
Off.
You're going to make a cost graph. Okay. So when you get a cost graph for display, when you start at 3, okay, when you start at 3, you get a cost graph, okay, for a displacement. This is one complete oscillation. That means at position 1, it is here. At this point, the second point, okay, where's the pendulum? The second point is already the displacement at the 0. That means the pendulum already come to the this position.
Center.
Then the third one, this position is where? Is here, okay, the extreme. So it's going to be cost graph. Now you tell me, if I start the time at 2, T0, I start the stopwatch at 2 and the pendulum is just passed at the center and it's on the way moving to the right. Okay, start 2. How's the displacement graph going to look like?
Sine graph.
It's going to be a sine graph. Good. It's going to be a sine graph. At 2, displacement is 0. Okay, so you're going to make a sine graph for the displacement. Okay, good. This is for when the time start at 2, the position 2, position 2. How about if start at 1?
Negative cost graph.
Ah, very good. So it's going to be a negative cost graph. It's going to be a negative cost graph or a displacement. Okay, so displacement time graph. So you have 3 versions, but the most common one is the first 2. Okay, it's either going to be a cost graph or it's going to be a sine graph. So displacement, we can draw a graph now. Displacement versus time. It's going to be a sine, cos. It's going to be trigo graphs. It can happen like a square wave also, but not in your syllabus. We have many types of oscillations, but the one in your syllabus is the one sinusoidal. Okay. So yeah, this is the displacement versus time graph. Okay. Okay. So now, because it's an oscillation, so it do have the property like a wave, because as I told you, wave produced by what? The origin of wave is actually oscillation. Kind of oscillation produces a wave. Sound wave is produced by your, okay, for example, light wave or any light wave is caused by electron movement. Okay, sound wave, continuous pressure, compression, and rarefaction produces a sound wave. So it's a type of oscillation produces a wave. So oscillation also has a property of a wave. So it has its own amplitude, period, frequency, and something called angular frequency. Okay, so we need to talk. I think this 3 is no problem: amplitude, period, and frequency. It's about angular frequency. Okay, what is angular frequency? Is similar as last time angular velocity. You know, last time angular velocity, omega in your circular motion, angular velocity. The unit is, formula is the same. Angular velocity, angular frequency, there is a slight difference. If anything move in a circular path or moving in an oscillation, okay, angular frequency only applicable for oscillation. Okay, frequency is only oscillation. How frequent? You come back to the origin. Okay, let's say I draw one complete oscillation. This is one complete oscillation. This is one period. This is one period. Okay, one period. This quarter wavelength, you can put it in a circle. You can put it here. The first one. Okay. The second region of oscillation, you can attach here. Okay, and the same thing. You go to the third one and the fourth one. So you can attach into one circle, So let's say from here to this point, from here to this point, okay. what is the angle it makes? So it's same as from here to here. This is the angle, angle. So anything oscillates, oscillates, we can imagine like it's moving in a circular path. It has some angular displacement. So we can come out how much. So when it go for one period, one complete period, okay, up to here, one complete period, it's like making a one round, making a one round. That means conclusion is one period is equivalent to like 2 pi radian. It's like a 2 pi radian, okay, like 2 pi radian. So omega last time in circular motion you learned what is the formula omega? Angular displacement, right? Angle divided by the time, if you still remember, under circular motion. Okay, so here we never call it as angular velocity, we just call it as angular frequency, how frequent it cover the angle. So other than that, it's similar as angular velocity, same equation and everything, just call it as a angular frequency. Okay, so if oscillation has a period of t, the omega going to be what? You still use 2 pi over t. You're going to use 2 pi over t. Okay, like your angular velocity. Okay, so this is something new. Every oscillation has its own angular frequency. If angular frequency is big means, if the angular frequency is big means the oscillation period is longer or shorter. If angular frequency omega is big means it cover the angle very slowly. It cover the angle very slowly. That means the oscillation is quite slow. When the angular frequency is quite big means, that means conclusion, you should know that the period is getting smaller. Okay, the period is smaller. Okay, and yeah, the period is smaller. Okay, big angular frequency. That means frequency is higher frequency. Okay, so this is some introduction about oscillation. Everything amplitude, period, frequency same, but you have something new called angular frequency. Okay. Okay, so this diagram can tell you like there is spring is oscillating up and down. Okay, so the spring is at the center. It traces the displacement graph like this. That means, can you tell me, time starts 0 at where? At the time starts 0 at here. Time starts 0 at here, at this location. Okay, at this location. Okay, this is 0 displacement. Okay, that's stated here 0. Okay, it's a 0 displacement. And the spring goes up to here, it achieves 4. Okay, 4. So the graph traces a sine graph. Okay, so of course from this graph you can get amplitude is 4, period is 10, and frequency is 1 over period. So you get 0.1. No problem about that. Now something new. They will ask what is angular frequency? Angular frequency 2 pi f, or you can use what? 2 pi over t. Okay, you can use to find angular frequency. So it's found to be 0.63. The unit for angular frequency is same as angular velocity, radian per second. How many radian it covers per second? Okay. So this is how we analyze. Okay. So I think the discussion is going to be similar as your oscillation. Okay, so similar as your wave. In your wave, last time you have phase difference. So oscillation also has its own phase difference. Okay, it has its own phase difference. Like you see, the brown color here. I think we imagine pendulum. The pendulum start at 0 for this wave. For this wave, pendulum, the time start from 0. Time starts 0, and the pendulum is at equilibrium because the graph is about start at equilibrium. Okay. So how about the blue one? Blue one. So the blue one is started here. That means, let's say it's a pendulum. The blue one is where? At the equilibrium, at the positive displacement or the negative displacement? The blue one. Come on, give a try. Blue one is at the positive displacement. Okay, it should be at a positive displacement. Why? Because the displacement is positive. This is a positive displacement. So, what is the phase difference between these two oscillations? These oscillations start at 0 when the time 0. These oscillations start from the age when 0. So these two pendulum phase difference. How do you find phase difference? So like last time, you take the two crest separation. Let's say because let's say this is in terms of time. Let's say it's time, time, time. So how do you find the phase difference? Anyone? Phase difference equals to what over what? T over
Yo.
period times 2 pi. Use this back to find the phase difference. Or what is another phase difference formula? If this is in terms of displacement, this is in terms of displacement. Sorry, displacement. So x. So it's going to be what? X over what? X over lambda
Times 2 pi.
So recall back lah. So they have phase difference. They have phase difference. So how to find phase difference easily is these two graphs you must plot, then you can find the phase difference like normally you do for the wave lah. Okay. Okay. If one pendulum starts at this extreme, okay, T0 at the positive extreme, displaced to the right, we consider positive. Another pendulum start at the negative extreme, T0. Okay. What is the phase difference between these two oscillations? Anyone?
Pi radian.
Yeah, pi radian. Yes, very good. It's a pi radian. Pi radian. Okay, if you plot this graph, going to be what? The first one going to be what? First one going to be like a what type of graph? If you draw displacement versus time. If you draw displacement versus time, this graph going to look like going to be a cos. Going to be a cos, and this graph going to be what?
Negative cos.
Going to be a negative cos. Yeah, it's going to be negative cos. So if you know phase idea, the phase difference is going to be pi. It's pi radian. So all the oscillations as something called phase difference. You'll ask in exam, phase difference. So you draw the what do you call the wave pattern, displacement versus time. You can get the phase difference. Okay. Any questions from here? Can so in phase. Okay, so now we come to the main part of the topic. Okay, something called simple harmonic motion. Okay, okay, what is simple harmonic motion? Very common question in the last exam. What is meant by SHM? SHM, simple harmonic motion. Okay, okay, simple harmonic motion. Let's say you have oscillation like Malaysia like oscillation, like your Selangor is like SHM. It's your like SHM. So SHM is like as a subset of oscillation. Okay, SHM is a subset of oscillation. It's a small part of oscillation. It's a type of a unique oscillation. Not all oscillations are SHM, but all SHMs are is a type of oscillation. Okay, pendulum movement is we know it's oscillation. It's an oscillation. We know it's oscillation, but SHM also categorized as SHM, simple harmonic motion. Spring oscillation, spring oscillation is also SHM. Okay, heartbeat like laptop or whatever the sound. This is not SHM. Okay, SHM means the graph must be like a sine or cos graph, the displacement graph. Then it's an SHM. If the graph of the displacement graph is not like a sine or cos, like a square wave, like a heartbeat signal, or any other pattern other than sinusoidal, then it's not SHM. Okay. So what is meant by SHM? The definition. This is you have to remember. So what is SHM? SHM is a type of oscillation where the acceleration is directly proportional to the displacement. This is the shortcut. The acceleration is directly proportional to the displacement and directed towards the equilibrium point. Okay, what does that mean? Okay, okay. To explain this, I go for pendulum. I go this pendulum. I think I better go for, I think spring better. Okay, we go for spring. A spring, you see spring. Let's say this is the equilibrium position. Equilibrium. This is your equilibrium position. Equilibrium position. Okay. So at this point, let's say the spring is extending down. I put a mass here. So let's say it's going down. Okay. Tell me, on the way it's going down, the displacement, let's say rising, the displacement of course rising. And the object is at the bottom here. The force, the tension is acting up. Then what force acting down? The weight of the mass acting down. You tell me, at this is the position 1 here, this is the position 1, this is the position 2. Tell me at which position the net force is highest. At which position the net force is highest? At 1 or at 2? Where the net force is highest? Anyone? When the spring goes down, what happened to the tension? Tension increases a lot, right? It does not change. So at this point, what is the net force? Net force is force up. Tension big or weight big?
Tension big.
Tension is big. So what is the net force formula? Tension minus weight, right? So I think the position at lower, always tension minus W is your net force. At which position the net force is the largest? At the lowest or the highest? At the lowest or at close to equilibrium? Yeah?
Lowest.
At lowest. At lowest, the tension is the highest. Because, you know, it's spring what? So it's Kx, right? Kx, greater the extension, okay, greater the extension going to be the big tension. So at the lowest tension, the net force is highest. If net force highest means the acceleration going to be highest at where? At the lowest or at equilibrium?
Lowest.
At the lowest, acceleration is highest. So acceleration is proportional to displacement. More you displace down, more bigger the acceleration. More bigger the acceleration. But the acceleration and displacement are in opposite direction. The negative tells is opposite direction. Why is opposite direction? Why is opposite direction? You see, at the lowest point, let me draw here back the spring. This is the lowest point. Okay, this is the lowest point. At the lowest point, you have tension, you have the weight as usual. Okay, tell me, the net force up or down? Net force is up. Acceleration up or down? Acceleration is up. But the displacement is where?
Down.
Displacement is down. Okay, remember in SHM, acceleration and displacement always in opposite direction. If acceleration up means displacement will be down. And the spring is compressed. When the spring is compressed and the mass is here, because it's oscillation what? The mass going to oscillate from up to down. This is equilibrium. So when the mass is here, okay, the acceleration will be down. Okay, because tension going to be smaller, weight going to be higher. But the displacement is where? Displacement is displaced up. Okay. So this is a very critical feature of SHM. Acceleration is always directly proportional to displacement, but in opposite direction. You can say direct towards the equilibrium position also. In opposite direction also. This is SHM. Okay. So what is SHM? The A must be proportional to displacement, and the A and X must be in opposite direction. Okay. For the A get bigger when displacement get longer, the net force must get bigger. This is SHM. Okay. Okay, now let me introduce you some system. You tell me, is it an SHM or not? Okay. I clear this. Okay, let me go to the okay. So I'm going to draw some oscillation. You tell me, is it an SHM or not? Okay, first is the pendulum. Okay. Plus, you can see the whiteboard, right?
Yeah.
You can see the whiteboard. I already draw a pendulum, right? Okay. So in this pendulum, you see this in equilibrium. Sorry, in equilibrium. So, and the pendulum get further. You have a tension here. You have a weight here, mg. Okay. So this is theta. Okay. So therefore, this will be theta, right? Okay. Tension. What force trying to pull it back? Anyone? The mg or the tension? This is 90 degrees. Which force pulling it back? Which force trying to restore it back? The component of the mg. So this mg, you resolve this direction, mg cos theta, mg sin theta. You open the angle or close the angle. This will be mg cos theta or sin theta. See, this is the, so you bring here, so you open the angle, right? You open the theta, when you bring here, so it's going to be sin theta. Okay, it's going to be sin theta. Okay, now tell me, is it this is an XHM? When the displacement increases and the x increases, that means the pendulum, let's say, go more further here, and the x increases. Okay, what happened to the force trying to restore it back? Is it increases?
I think so.
Sine 30. Let's say this is 30. Oh, okay. Okay, class. Yeah. We will be starting this discussion back after 40 minutes. You take maybe 3 minutes. I send another invitation later. So you join back. Okay. Today 2 hours one. Okay. So we'll join back later, or if it stops. Okay now. So when the pendulum is at this location, the angle is increasing, right? When the angle increasing, the sine theta value get bigger or smaller? Getting bigger. So the force getting bigger. So force increases, that means, and displacement increases. That means A proportional to displacement, but in opposite direction. You see, displacement positive, but acceleration is this way. Okay. And the pendulum is at this corner. Displacement is positive or negative? Displacement is negative, but the acceleration is this way. Displacement is negative. So is this an SHM? This is a SHM. Why is an SHM? The acceleration is directly proportional to displacement, but in opposite direction. Okay, so this is an SHM. Okay. Okay, now I'll be giving you more. Okay. So let me show you another system. So let's say you have a tube like this, a tube like this. Okay, sorry, not this tube. I go to this a platform. You have a marble. Marble is rolling down from here to here, here to here. Okay, it's rolling down. Okay, it's a nice smooth curvature track. Is it an SHM? Is this is an SHM? Okay. Anyone? Is it an SHM? SHM means what? Acceleration must be directly proportional to displacement. That means when the object moves away from origin, this is origin, this is the displacement. Okay, and the particle move away from origin, the force must increase. The force which trying to restore it back must increase. If it increases, then it's going to be SHM. If the force trying to restore it back, is it increased? How to know? What force trying to restore it back? Can you draw the free body diagram for this pendulum, for this marble? What are the force acting on this marble? The weight acting down, you have the weight. What else acting? What force is this? Reaction acting this way. Okay. So yeah, the angle it makes, you can say the angle this makes is here. Okay, the angle is here, theta. Okay. So okay, theta. Okay, this is the force on that marble. Can you tell me what force trying to pull it down? Anyone? I think it's similar to this pendulum. Can anyone tell me what force trying it to pull it down? The component of the R or the component of the weight?
Wait.
Weight. So W sine of cos theta, try to restore it back. This is W, this is a theta. So this W you bring here, you open the angle. So it's going to be sine of cos.
Sine.
It's going to be sine theta.
Fine.
It's going to be sine theta. Okay, good. So now tell me, is it an SHM? When displacement increase, is this force increasing? When the pendulum move further up and up and up, further up here, what happened to the angle? The angle get larger or smaller?
Larger.
When angle get larger, so the force W sine theta getting bigger or smaller? Getting larger, right? Sine, I think sine 30, sine 60, I think sine 60 is bigger, right? So the force getting larger. Is it an SHM?
Yes.
Yes, this is an SHM. Why is an SHM? Because force increases with displacement. That means acceleration is proportional to displacement, but in opposite direction. Opposite direction, right? You see displaced to the negative, but acceleration is to the right. When displaced to the positive, the acceleration to be to the left. Displacement here, but acceleration is here. So opposite direction. So this is an SHM. Okay, this is an SHM. Okay. Okay, now another one. Okay, this is my Form 5 actual practical SPM. We have to do our own practical last time, so practical paper. So they give me a pipe, a small transparent pipe. They ask us to make it like a U shape, use a retort stand at the side. They ask us to fill up with a liquid, a color liquid, red color liquid. So it achieves the equilibrium here. Then what they ask us to do is, they ask us to blow at one edge. So until what happened? The level of the water on one side rises, okay, rises, yeah, okay, so rises. So of course, here the water level will drop down, okay, drop down. So this is the new liquid position. Then they ask us to let it go, let it oscillate. So the water level going to oscillate. This will go down, this will go up, then vice versa is going to oscillate. Okay. Then they ask us to find the period and ask us to find the acceleration. That's another story. But now what I'm going to ask you is this movement is an SHM? Okay. I give you 1 minute for you to think. Is this an SHM? When the water level goes up, you check the force which trying to restore it back, trying to pull it back. Is it increases with the displacement? Is it increases with displacement? Okay. So is it an SHM? What do you think? Let me show you. Okay, so at this level, this level, this water level, this is the water level. the weight of this water, which is just above, the weight of this water just above the equilibrium position is the one contribute to push the, what do you call, initiate the oscillation, the weight of the water level above. So if the level rises more further up, what happened to the force which trying to restore it back, trying to push it back? Increases, right? More water level, more above water level. Okay. So when displacement get bigger, the amount of water level on top is getting bigger. So we said the force which trying to push it down increases. So this consider also is an SHM. This is an SHM. So we said acceleration is still proportional to displacement, but in opposite direction. Okay, the weight acting down, but displacement is up. Okay, so this is an SHM also. Understand this part? It's a unique question. More higher the water level it goes, more greater water on top. So more heavier, you're going to push the water down. So it initiates the oscillation. More water above, more weight, more force, push it down. So it's an SHM. More higher the displacement it goes, more force. So it's an SHM. Okay. Okay, now fourth one, the last one. This is an SHM. Sorry. Okay, undo. Okay. It's a kind of a V-shape, straight platform. You have a marble here going down. Okay. It was as a specific angle here, same angle. So the marble goes here and come back here. This is an SHM.
Yeah.
It's an SHM.
No.
When displacement increases, this is the force trying to restore it back increases.